Hello everyone, my name is Ferhat Özgür Çatak. I am an associate professor at the University of Stavanger, Norway. My presentation title is a cryptographic federated learning-based channel estimation for next generation networks. You can access the implementation from my GitHub repository. This table shows the KPI and compares the KPI of 5G and 6G. There are several key performance indicators in the table. As you see, as an example, peak data rate in 5G is 20 gigabit per second, but it would be 1000 gigabit per second in 6G networks. Similarly, the maximum channel bandwidth is 1 gigahertz, but it would be 100 gigahertz in 6G networks. In order to achieve these key performance indicators, we have to follow the new solutions. For example, we have to develop new spectrum usage and radio design paradigms. Also, we have to use novel network architectures. Also, we have to apply enhancing network coverage beyond the terrestrial domain. Lastly, we have to use increasing intelligence and automation, which is artificial intelligence. This figure shows the potential usage of artificial intelligence algorithms at different layers of wireless systems. Basically, there are two layers, physical MAC layer and network layer. Here, in this research, our focus is physical layer, and it's one of the development, which is channel estimation. There are 4 different components in our research. The first one is dataset. We generated channel estimation dataset using MATLAB 5G toolbox. The second component is deep learning model. We developed and trained convolutional neural network-based semantic segmentation to build the prediction model. Third component is trustworthiness. So our research focus is the privacy in AI models in wireless communication system. And as the mitigation, we employed the homomorphic encryption based federated learning. I will explain the details. This is our dataset. We use MATLAB LT and 5G toolboxes to generate the channel estimation data. We generated 256 training data using the MATLAB for transmit and receive the signal. And each data in this training data consists of 8,568 data points because there's only one antenna and the subcarriers, the number of subcarriers is 612, and we have 15 OFDM symbols in this data. And each data point in the dataset is complex values which has real and imaginary parts. Then we converted these complex numbers into the real numbers. This figure shows one example from the datasets. The first figure shows the normal input. The second one is the actual channel, and the last figure shows the predicted channel based on the normal input. And this is our deep learning model for channel estimation. So we train this deep learning model to estimate the channel characteristic for improved signal reception. And we used MSE, mean square error loss value, to find out the prediction performance of the final or global deep learning model. So, what is homomorphic encryption? I will try to explain it with a very simple example. Let's assume that we want to calculate the rectangle area using cryptography. Let's assume that we have a rectangle and width information is 7 and height is 3. So it is very simple. The area is 21, the multiplication of 7 and 3. But here in this example, we will try to calculate this area in cryptographic domain or in the cipher domain, encrypted domain. Okay, the first step is to create the public-private key pair in the cryptography algorithm. These are our public and private key pair information. After that, we can encrypt the first information with information. If we follow the encryption procedure, then we will use the public key information, 23 here, 143 here, then we will get encrypted 2. And we will use the same procedure for height information, which is 3. If we follow, then we will get 126. 126 is the encrypted representation of the 3. Then in the public or in the cloud, we can multiply these two encrypted data and we will get 256, 52. After that, we can perform the decryption. Then we will get 21, which is same as the original plain multiplication. This is our system model. In this system model, we assume that there are several base stations, and this base station, they have their internal data set, and they don't want to share this information with the other base stations. Also, they want to protect the local models from the server, from the aggregator, or from the cloud server. Because there are some reverse engineering attacks, then the cloud server could regenerate the training data from the model. There are several existing attacks, known attacks, how to generate the training data from a trained model. So by this way, by applying the encrypted models in the client side, we are also protecting the model from the aggregator, from the cloud. Here, according to this figure, each base station is responsible to train a local model here. Then there is a model encryption using the public key of the using homomorphic encryption. Then there is an encrypted model, and this encrypted model would be sent to the aggregator aggregation server. So after each base station sent the local models to the cloud or aggregation server would perform these arithmetic operations, homomorphic additions and multiplications. The idea is very simple. There are, for this example, there would be 5 different model weights. So there would be 5 additions, homomorphic additions. This is completely different from the plain text addition. There are homomorphic additions. After that, there is a division. Unfortunately, there is no division operation in homomorphic encryption. So we need to convert this division operator with multiplication. After that, the aggregator will calculate the global model, encrypted global model. Then the cloud or aggregation server would send this encrypted global model to each base station. Then each base station can decrypt this encrypted global model using the private key. These are the algorithms on both client and server side. As you see, in the training phase, each client is responsible to perform this training phase. This is just a simple deep learning training phase. But here, there is an encryption and also homomorphic addition operations on client, on server. We performed several experiments using this algorithm, using this method. First, we used the federated learning without encryption, without cryptography. And this is our prediction performance based on MSE, mean square error based prediction performance metric. And then we encrypted the model, but we didn't use any federated learning. This is our result. And these are the encrypted federated learning with 3 clients, 4 clients, and at the end with the 9 different clients. According to this table, the best model is without encryption, of course, as expected. Because in encryption, if we apply homomorphic encryption, then we will get some loss at the end, because the homomorphic addition is not the exact, will not generate the exact solutions, exact results. Instead, it will generate some approximation. So there's a loss in the computation. The loss is very small, but still there's a loss. So the prediction performance, the expected prediction performance would be lower than the without encryption. But here, according to this table, the results are very similar, very close to each other. So these are the acceptable prediction performance degradation. Another issue with the cryptography is the execution time. Because in the homomorphic domain, the addition and multiplication operations are completely different. There are several functions, and they are responsible to perform this addition and multiplication procedure. Then we will get a overhead execution time. So these are our execution times in number of in seconds. So for 3 clients, we executed this federated learning around 250 seconds. For 9 clients, it would be around 550 seconds. This is our observations. We proposed a cryptographic homomorphic encryption-based federated learning for channel estimation in next-generation networks. The important observations are, with federated learning approaches, cryptographic federated learning approaches, training models across decentralized edge devices, and effectively secure AI models and user data. The second important observation is the number of clients does not significantly impact model prediction performance regarding mean square error. Also, federation learning iteration stability improves with the increased iteration length and irrespective of the number of clients. This is our summary. In this research, we combined homomorphic encryption with federated learning for channel estimation in next-generation networks to ensure a secure deep learning training environment. There are several key points. The most important key point in this research is MSE, or prediction performance results. So the prediction performance or model performance with and without encryption, they are very close. Also, there's a performance key points. So there's a competitive performance with notable trade-off in training time and client numbers. The most important part of this research and the experimental result is privacy concerns. So a combination of homomorphic encryption with federated learning emphasize the need for safeguarding base station data and deep learning model privacy. So here we are not protecting just data, also we are protecting the model weights from aggregator, from the server. This is the end of presentation. Thank you for listening.